Welcome to Advanced Embedded Systems. This is lecture 28 where we'll talk about digital low-pass filters. Don't forget to do your time logs. There's a link on the Canvas page to a Google spreadsheet where you can update your time logs as you go. Project proposal revisions are due today. Hopefully you took a look at the rubric posted online as well as the template. Make sure you update it based on my comments. If you didn't update it, make sure you're looking at those template and rubric to make sure you're not losing points on your proposal. All right, so we're going to talk about digital low-pass filters and digital filters in theory. So we're going to be talking about how we build filters. We're going to build a filter called an infinite impulse response filter, IIR, because it's given an impulse and as an input signal, it'll ring forever, have infinite impulse responses. This IIR is from within a broader class of filters called biquadratics, so named because they have two quadratic equations in them. We're going to build a version of the analog filters that we talked about last time. Process of this is a block diagram of a digital biquad filter, and you can take a look at the website linked here. More information on those biquad filters at your leisure. Some things to note about this block diagram. You have these blocks called z to the minus 1. These are basically delay function blocks that delay y of t to y of t minus 1. So you have delay 1 and then delay 2. Same with the x input, and it's going to apply these functions as we go. And the other things you need to know, you have these triangles. Those are multiply blocks where it's multiplying x of t times this coefficient b sub 0 and x of t minus 1 times b sub 1. And all these get added together with these summers, which are these plus signs in the circle. Those add them all together. Thus, we get our filter response for our output. And that can be generalized in an equation. Y of t is equal to x of t times b sub 0 plus x of t minus 1 times b sub 1, x of t minus 2 times b sub 2 plus the negative coefficients. So it's basically subtracting y of t minus 1 times a sub 1 and y sub t minus 2 times a sub 2. These coefficients that we'll talk about, these multiply parts, depend on the frequency, cutoff frequency we want for our filter, f sub 0, and f sub s, which is our sampling frequency. And our audio codec is 48 kilohertz, so that is our sampling frequency. If we assume, which they're not, but if we assume our coefficients are 2.16 format and our x of y and x of t, or x of t and y of t are, those feedback forms are 18.0, the product would be 36 bits. A 20.16 output, we're basically adding the whole portions of that product. For our filter demo, the coefficients are actually Q2.30, and our x of t and y of t are 18.0. Those will be coming, basically translating to 18 bits for our output to our audio codec, which is 18 bits wide. We use the product of that, Q2.30 and Q18.0, we get 20 bits of whole and 30 bits of fractional portion. We're only going to use the least significant 18 bits, and I'll show you how that is, where that is in the code in just a little bit. I'm going to walk through how that works. So, use those 18 bits. A note, all synchronous systems have history, so they all have feedback to the inputs, and that's how synchronous systems work. So if you go and download from the website the spreadsheet, just download lecture28.xls, open that up, and enable editing. Once you download it, go to the second order tab, and this is what we're going to go through first. So as you notice, based on the upper left-hand corner, that frequency, the f sub 0, the cutoff frequency, or the actual frequency of the signal, the response to that signal at that frequency is set in this top left corner. You have x of t, that's our input, and that's the red trace displayed here. Y of t is the output after the frequency response. So you're going to get some phase shift and amplitude attenuation based upon the filter. The filter is defined by those 5 coefficients that we talked about before, and y of the other coefficient is just 1. Those coefficients determine how the filter will behave, and there's a tab called coefficients where you can actually update that value. So you can go and take a look at those. Right now, the coefficients are set up with 300, but if you had it set up as 100 or at 1 kilohertz frequency cutoff, then it would update those values. So this shows 1 kilohertz cutoff frequency, and our frequency sampling of 48 kilohertz, we get these coefficients for a low pass and a high pass filter, depending on which one we're doing. Notice they match what I have here. And all you have to do is adjust these two values, and you can change the characteristics of the filter. Before we get into that, I can show you, play around with the spreadsheet, but you can actually set it up so that it'll automatically update the coefficients. Just set it equal, and you can actually link to those values here. Right now it's set to the same value, so it's not going to change the coefficients for our system. So t minus 1, x of t, x of t, and y at t minus 1. Did the wrong. T minus 2. And then y of t minus 1. Plug those values in. Notice we have the same frequency response, but if we changed our cutoff frequency to 300, obviously at 1 kilohertz, we'd have a lot more attenuation. Notice the attenuation of our signal. But I'm going to set it back to 1,000. 1 kilohertz for right now, because what we're going to be doing next is actually going to be updating that. So, that third tab we have, basically, and it's slightly updated from what I show in the slides, but you get the same idea. You have a fractional portion, and then it converts it to a Q2.30 fixed point value. The way it shows up is not necessarily all hex, but I did your fixed point graph, should be about the same. So you plug in those coefficient values, and you get the converted hexadecimal values for those Q2.30. The only note is the first 2 bits are actually the binary first two bits for the coefficients. So you have 0.00392, and that value is this coefficient. So you see 0, on your first value, the 2 bits, and then we do an underscore just to define it. So these are the first 2 whole bits, and then the other 30 bits are the fractional bits. This next bit shows you have 8 bits here for 32 bits. It shows the other 2 bits, which is 0, 0, 0. So I'll show you the negative one just so you can see what it's like. When I do negative 1.8, those first 2 bits are 1, 0 because it's a negative number. And then the last 2 bits are going to be the 0, 0. So 1, 0, 0, 0, and then B, D, 1, 7, 3, A, and 2, just like it's shown here. So you can use those values to and the spreadsheet to actually convert those values to a binary equivalent for the coefficients, and we're going to use those data values to plug in as coefficients to our filter and see the frequency response. So this code is the left side of that biquad. Notice it actually takes those coefficients for a 1 kilohertz cutoff frequency, and it inputs those values as a binary value. The underscores don't really count, it's just there for visualization. And in the comments I put the decimal values for each of those coefficients. So we have coefficient B0, B1, B2, A1, and A2. Notice B2 and B0 are the same value. The rest of it, we're using this second order Butterworth filter from DigiKey, the code, and we're port mapping it in. So we plug in the coefficients, and then we can get our ready signal coming off of the audio codec, and then we're going to have our ADC output from the audio codec wrapper, and then the output filter response. So there's a done signal and then an output filter response. This is essentially how it's all hooked together, a block diagram. So we have our audio codec wrapper, the left channel, there's a left and a right. I only show the left in here. So left input, left ADC value goes into our filter in the X in, and then our ready signal goes into the trigger, and then it outputs this value. And then we have the L out value is going to be determined by a mux, where if the value of those 2 slider switches is 0, 0, we're going to have basically loop back without the filter. And then any other slider switch, 1, 2, you can actually set up. So you can, for the homework, you're going to set up 1 filter, but you can actually set it up to output different filter responses on the left and the right channel based on those slider switches. So I set it up for you to actually put in those different conditions. Right now it's just a low pass filter of cutoff frequency of 1 kilohertz. So if you actually take a look at those, the demo, this shows the left filter and the right filter both set at 1 kilohertz here, and you have your audio codec wrapper, how it is instantiated, and then we have this little process down here. If reset is 0, we set it to 0. Otherwise, if 0, 0, we're going to have no filter, essentially. All other conditions, which you can actually have it set up so you can separate the left channel and the right channel with different slider switches. Right now they're just outputting at 1 kilohertz cutoff frequency, putting a filter on there. The filter block, if you take a look in there, there's a lot of code in here, but the big things that you're going to want to pay attention to is these outputs are, again, 50 bits wide for the product because we're multiplying out our values. And then our output, Y out, is only 18 bits. And notice I showed you before where it's basically going to multiply these things together. And then the output, Y out double, notice we're actually doing taking the lower 18 bits of each of those whole portions, so not up to 49, so 47 down to 30. As we're multiplying through, you can see these are the products. So we're taking the coefficient times the x sub 0 and x sub 1, x sub 2, multiplying those out. These larger values are 50 bits wide, but then we're truncating it down to these values to get our outputs out there. Long story short, it's essentially just implementing the equation that we talked about in the slide, this equation. So it's multiplying this out to get our filter response. So we're going to, first thing we're going to do is we're going to use that spreadsheet to generate the table listed here based on the input frequencies. We're going to plot the phase and magnitude. Your slides should show something like this, where it takes that first value, given 100 hertz, and the frequency response for the filters. We still have our coefficients for f sub 0. Cutoff frequency is 1 kilohertz, and our frequency set to 100. We're going to get a gain of negative 0.00045 shown in the slides, and then a phase of 8.25, and it's going to plot those values. I already have it plotted. You can actually use these Bodhi plots if you want to plot them as you go. Otherwise, you could also right-click on this data and you'll see the solutions. But I do want you to go through and set those values and find out what you're going to get. So if I type in a 300, frequency of 300, this is my gain. So I can just copy that into here, get my gain. And then get my phase, plug those in here. Maybe I'll just plug them in. And then next frequency is 500. 500, type that in. We're going to get more of a gain, a negative gain, so a more attenuation as the frequency will increase. Our phase is also increasing as we go. Eventually, you're going to get these values right here. So you're going to keep gaining as you increase your frequency, more attenuation as we increase it, because it's a low pass, so lower frequencies pass more values, and then it attenuates more as you increase the frequency to 15 kilohertz, and then your phase is also increasing till it gets pretty much to, notice, 15K, we get quite a bit of attenuation, or phase, and quite a bit of attenuation. So the Bodhi plot, and again, you can take a look, just edit the data, and it'll open up the spreadsheet where I plotted that for you, just to make it easy. A matchup for gain, and then the phase plot as well, match up as well. So, given that, go through, make sure you understand how those work. Then we're going to go through and actually create, we're generating the coefficients for a 500 hertz signal. And then you'll do one on your own for a 300 hertz signal. And that will be part of your homework. So let's generate the coefficients. I will show you how to do that. Come in here, we get a frequency 0 for 500 hertz cutoff frequency. My coefficients value, I'm just going to go ahead and copy these. Copy it, paste it down so I can create a new other one. And I'll just say for 500 hertz signal, you'll do the same for a 300 hertz signal. And I'm going to say move it up to my coefficients tab, 500 hertz, so x sub 2, got this value. They're a little bit out of order, but it really doesn't matter because throw in the values, x sub 0 and x sub n minus, or t minus 0 and t minus 2 are essentially the same, so it doesn't matter what order you copy them in. Then the coefficients for y t minus 2, and those are out of order. Those do matter, so I'll copy the first one in and then paste it up. All right, so we can take those values and we can start converting them. You start plugging in the values, so that's the first value. We get 0, 0, 0 for the first bits, and then the lower two bits are 0, 0. I get 0 for the next nibble, then a 1, 0, 0, 1, 0, 1, then 0, 0, 0, 0, C, 1, 1, 0, 0, 0, 0, 1, 1, B, 1, 0, 1, 1, and then 0, 0, 0, 0. This is going to be the same value as the third value. Now we need to figure out the second one. We can get a, copy the decimal value in there, the fractional portion, and we get 0. Second nibble is zeros. Third, wait, I don't have 0, 0, 0, 0, 1, 0, 1, 8, 7, 5, and F. Last nibble. Y sub 9. Copy this value in, or get a fractional portion. We're going to get a 1, 0, 0, 0 for that first one, so at bit 8. Then 5. E 1110. One zero one 011 for 7. E and C. Last one, copy the last fractional portion in. You're going to get a very similar value, 0 for the first 2 bits, then 3. We get 1010 for A, 5, 0111, 7, 1010 for 9, 0, 7, 2. Notice that is also what we get here. Should look the same. Stop doing that. We're gonna post this and get to our lecture. All right. As we have C here. All right, so plug these values. Take these values that we calculated, our coefficients. You're going to plug those into the right channel on your lecture. So you're going to get this demo. You're going to plug those into the right channel here and put in the values. Make sure you update the decimal values as well for those coefficients. And then for the 300 hertz, you're going to plug that into the other channel, say left channel. So you're going to have 2 different filter responses in there. And you're going to go through and you're going to figure out the coefficients for a 300 hertz signal. And so in the homework, complete that development. You're going to do a cutoff frequency of 300 hertz and find those Q2.30. So you're going to type in 300, find these values for the low pass filter, and plug in your binary coefficients to get your binary coefficients for the left channel, and take the other ones for the 500 hertz signal and plug those into the right channel. And you're going to make sure it works on your board. You can actually play some music through there and listen to the filter response. And it'll cut off either 300, anything below 500 or 300, and you can set up your switch statement at the bottom. So different switch values would essentially disable the right channel, the left channel, and apply the filter response for that. Update that and push it to Bitbucket. Build a project around that and make that work. Build it and see what it looks like. And listen to the difference in music. So you're passing the lower frequency, but you're going to be killing some of the treble, some of the higher frequency signals. So some of the voice and things like that, depending on the filter response. So that concludes the lesson for today. Once you get that done, you should get some values that look similar to this. But make sure you do your homework and post that